This is lesson 2 of the first unit. I'm looking at page 8 of the notes, and partway down it says a function fails to be differentiable at x equals a for a variety of reasons. I want to start with some drawing. Let's make sure my pen works here. So in this particular drawing, I'm going to make a function that's like this, and it continues on forever to the left, but it's not smooth here. And this has a mathematical name, believe it or not, just called a corner. So a corner is a point where it's not smooth. We might draw another one, a traditional V shape, perhaps like an absolute value or something. So these are both examples of corners. So the question is, let's first write corners. Corner. Question is, mathematically, what's happening to make it a corner? What's happening to not let it be smooth? The fact that it's not smooth at these corners makes it not differentiable. But we can see, let's pick another color. We can see that the slope here is approaching, let's say like positive 2 or 1, something positive. But as we approach from the right, slope is approaching a negative number, perhaps -5. So in order to have a corner, we say that the two one-sided derivatives are different, and that's a new terminology, and that's what the top of the page is describing. So if we take a moment to go to the top of the page now, and I'll scroll down to resemble the top of the page, and let's go back to white. It says that the limit as h approaches 0 from the right of f of a plus h minus f of a all over h, provided that that exists, we're going to give it some notation, and this notation is not in your text, but it is standard notation, and I'll write f prime at a, but this is approaching from the right, so I put it in the sub, and it means the one-sided derivative. And likewise, f prime of a from the left means the limit as h goes to 0 from the left of f of a plus h minus f of a. This is like one of the examples we did in lesson 1, but just now giving it some formal notation. So coming back down here to the corner, we can say it's a corner if the following occurs. We have f prime of a from the right, and also f prime of a from the left, both exist. And at the same time, or but, f prime from the right is not equal to f prime from the left. Not equal. If that is the case, you have a corner, which is what is shown here in the drawings. Next, we have what's called a cusp. Now, cusp is like an extreme corner. It comes up and goes back down. Perhaps if you were drawing like a bird, a seagull or something, you might draw it like that. Now, what makes this cusp different than the corner is the fact that not only do the two one-sided derivatives differ, but this slope, you see, maybe this is positive 2, and then it's positive 5, and then positive 10, and really large, really large. This is actually approaching infinity, positive infinity. And as we approach from the right, it's approaching negative infinity. So it's an extreme corner. So the criteria mathematically for this cusp is that f prime of a from the right approaches positive infinity, and at the same time f prime of a, as we approach from the left, is approaching negative infinity. So that's one way we can have a cusp. Or, on a flip-flop, f prime from the right of a approaches negative infinity, and f prime of a, as we approach from the left, approaches positive infinity. So if you have the first bracket or the second bracket, you have a cusp. Finally, we have what's called a vertical line tangent. So let's see if I can draw this appropriately. That might not be good enough. Let's see if we can explore. If I drew it right, there should be one point where the actual tangent line is a vertical line. So we approach from the right, it's approaching positive infinity, and from the left, it's also approaching positive infinity. An example of this might be something like y equals the cubed root of x. Comes down, does this, kind of like that. So mathematical criteria for it is as follows: f prime from the right of a approaches positive infinity, and at the same time f prime, as we approach from the left, is also positive infinity. So that's one case. Or we have the case where they both approach negative infinity, like I have written here. The next three examples are about deciding whether or not the function is differentiable at a given point. This is again like the problem we did in the first lesson of those piecewise functions. So the question here is, does c prime of 1 exist? Question mark. And we begin. C prime of 1 from the right. Because we have a piecewise function, we're looking at the behavior of not the function, but the derivative from either side. So this is the limit as h approaches 0 from the right. We use generic c1 plus h minus c of 1 all over h, which equals the limit as h goes to 0 from the right of 1 plus h plus 2 minus 1 squared plus 2 all over h. Notice that c of 1 is c of 1 is c of 1, which is equal to 1, which is always the quadratic here. Alright, so this equals the limit as h goes to 0 from the right of, well, let's see if we can simplify. We have a 1 and a 2 minus 3, so, oh, good. That cancels out, h over h. Limit as h goes to 0 from the right of 1 equals 1. And we'll come over here. C prime from the left of 1 is the limit as h goes to 0 from the left, c of 1 plus h minus c of 1 all over h. You'll notice even in my rushing state, I will not fail, at least intentionally, not fail to write the generic before writing specifics. So now we have 1 plus h squared plus 2 minus, and then 1 squared plus 2, that's c of 1. And this is over h. So we have the limit as h goes to 0 from the left, 1 plus 2h plus h squared plus 2 minus 3 all over h. Keep on going here. Limit h goes to 0 from the left. We can factor out an h out of this. that. Some simple algebra. And this is going to leave us with 2 plus h, and the end, that equals 2. So we're going to say now that c prime from the right of 1 is not equal to c prime from the left of 1, and therefore the limit as h goes to 0 of c of 1 plus h minus c of 1 over h does not exist. Finally, therefore, c is not differentiable at x equals 1. And I'd like to end this by classifying this. Which type of situation is this? Corner, cusp, vertical tangent? Well, they both exist, but they're different. So it's a corner. Quick sketch of this would illustrate it further. So we have a parabola, let's see, intercept of 2, and then goes like this. The line is actually a continuous function. The line jets out from there. It is a continuous function, but because of the corner, it is not smooth. It is not differentiable at x equals 1. Example 2, we are asking f of x equals the absolute value of x, and we want to know whether or not it's differentiable at 0. So I'm going to say that f of x equals, this is review, x when x is greater than or equal to 0, the opposite of x when x is less than 0. Those are the conditions. Question is, does f prime of 0 exist? And we'll start off by saying f prime from the right of 0 is the limit as h goes to 0, f of 0 plus h minus f of 0 over h, which is the limit, h goes to 0 from the right, forgot that, from the right of, well, we plug in, we have 0 plus h minus 0 for h, which is going to give us the limit as h goes to 0 of 1, which equals 1. So it exists on that direction. F prime from the left of 0, the limit as h goes to 0 from the left, f of 0 plus h minus f of 0 over h gives us the limit as h goes to 0 from the left, and that's going to be the opposite of 0 plus h minus 0 over h, or it's the limit h goes to 0 from the left, oh, I forgot this right over there, of -1, which is -1. They both exist, but they're not equal. We have a corner. These two are not equal. Therefore, f is not differentiable at x equals 0. The classification is a corner. The graph of this is good old-fashioned absolute value v-shape. The slope is approaching -1 from the left, and from the right is approaching +1. Example 3, h of x is the cube root of x. Is it differentiable at 0? So does h prime of 0 exist? So let's move here. H prime from the right of 0. You know, this is confusing because I'm using h as the function, and I'm saying as h goes to 0. So I'm going to change this, instead of h, I'm going to say the change in x, which is what h is actually describing. I think this way we don't get confused with what h we're talking about. So we have 0 plus change in x minus h of 0 all over change in x. So that's going to be the limit as change in x goes to 0 from the right of the cubed root of change in x minus the cube root of 0 all over change in x. So we essentially have change in x to the 1/3 and change in x to the 1 on the bottom. So that's going to simplify change in x, 0 from the right, to be 1 over the change in x to the power of 2/3. So as that approaches 0 from the right, the values are getting smaller and smaller and smaller, smaller but positive, so the denominator is getting smaller and smaller and smaller, positive, which means this whole fraction is blowing up to be 1 over really small to approach positive infinity. And so h prime from the left of 0, the limit as change in x goes to 0 from the left, h is 0 plus change in x minus h is 0 all over change in x, which is the limit as change in x goes to 0 from the left of, let's see, what is this going to be? Same deal. Cube root of change in x over change in x, which is the limit as change in x goes to 0 from the left of 1 over change in x to the 2/3. Okay, so now we're plugging in negative values because they're to the left of 0. Negative values are getting smaller and smaller and smaller. But because of this 2 in the exponent, it's going to square and make everything positive. So it's 1 over really, really, really small positive still, which means this is also going to blow up to positive infinity. It's growing without bound. So does this exist? No. Does either limit exist? No. But we do know that they are approaching the same direction. So, well, let's look at this. Is this a true statement? Is that a true statement? The temptation is yes, because they're both positive infinity, but neither one is a real value. You can't say that something that is not real is equal to something else that's not real. So we actually have to say they're not equal to each other because neither one of them exist. And therefore, h is not differentiable at x equals 0. And the classification of this is a vertical line tangent.